Hello, all you seekers of physics knowledge. It is I. I am here to help you with multi-mass systems from an approach using dynamics. And let's get after this. The general strategy is to draw a free body diagram for each object. You can do this on the diagram that I have on the right, or you can redraw it. So I'm just going to do that really quick. For the 3 kilogram mass, you've got a tension force, and then we've got a normal force. How nice. We've got the force of gravity in the y. We've got the force of gravity in the x. Yes, one of these masses is on an incline, and because we might as well just get right after the tougher problems, we have friction. You're welcome. And there's a force of friction. Okay. I chose this example simply because there was the most going on, an incline and friction versus just a very simple, like, multi-mass system like this. I don't even know what that is, but you know what I mean. We ain't doing that. That's way too easy. Okay. The other thing that you should do in your diagram is label the positive direction as a direction it will move. Well, it doesn't say so in this. Oh, it does. It says that the 7 kilogram mass is going to fall. So if this is falling, down is positive for the 7 kilograms, and up and to the right here, up the x-axis here is positive. So this will be the positive direction for that mass. But let's draw a free body diagram for the other one as well. So you draw free body diagrams for each mass. This is my 7 kilogram mass, and we have tension, and we have the force of gravity. Simple as that. Don't forget to label your positive direction, because in this case, for the 7 kilogram mass, down is positive. As you know, with dynamics problems, they usually involve free body diagrams, some of the forces x, some of the forces y, and perhaps some kinematics. So let's do that. For the 7 kilogram mass, I will sum the forces that cause this mass to accelerate. Technically, it's the y-axis, but we have mg down minus ft up equals may. Again, gravity is down. So what I'm going to do here is I'll throw in some numbers. 7 kilograms, 9.8 meters per second squared, minus tension equals 7 kilograms. Not much we can do. Acceleration. That is a terrible looking kilogram. There we go. Not much we can do. We have tension and the acceleration. All right. For this one, it's getting pretty far in the year by now, I think, and some of you may know already that if I sum the forces in the y that cause this mass to accelerate in the y-axis for the inclined mass, there is no acceleration. So we basically have Fn equals mg cosine theta, or Fn equals, what was that mass? 3 kilograms times 9.8 meters per second squared times cosine 40 degrees. You would think that I would have done this before starting the video, but I did not because I'm a terrible person. I got 22.5 newtons. All right. That's nice. I still have to sum the forces in the x. So I'm going to do that here, and sum the forces in the x that cause the mass to accelerate in the x. Something to be aware of here. This acceleration in the y and this acceleration in the x, although one says x because the 3 kilograms is accelerating in the positive x-axis, and the 7 kilograms is accelerating in the y-axis. These are the same acceleration because they're attached to the same rope. So they have to have the same acceleration. So you can call them AX, you can just call them A, whatever you want to do. But here we go. We have a tension force up the hill. We have mg sine theta down the hill. We have mu times the normal down the hill, causing this mass to accelerate. And if I sub in some numbers here, I have ft equals, oh, sorry, not equals, excuse me. This will not be edited. This is going to take a second. Fast forward if you'd like as I fill in some numbers here. Sine 40 degrees. Friction is 0.35, or the coefficient is at least. So minus 0.35 times the normal force, which we got in blue there. How nice. causes the 3 kilogram mass to accelerate. All right, we're stuck here. Right now, we have two expressions with two unknowns. And you have choices here. This is totally up to you. But I believe we're solving for the amount of time it takes for this mass to move a certain distance, which means we need the acceleration, which means we should isolate tension forces. Now, you can either isolate and set equal, isolate and substitute, whatever your preference is. I'm going to isolate here and set them equal. The tension in the rope is the same as discussed in class. So Ft is going to be equal to 7 times 9.8, which I should be able to do in my head, 68.6 newtons minus 7 kilograms times A. I could take this, again, I could just take this and sub it in here. If that's your preference, do that, please. It doesn't matter. For whatever reason, I'm choosing to isolate this tension force. Call me crazy. 3 times 9.8, sine 40. And I get 26.8 newtons plus 3 kilograms times A. Again, up to you what you want to do here, but now that we have isolated the tension forces for both, we know that they have the same acceleration, the same tension in the rope. We can set the two tensions equal. So I can set Ft equal to Ft, if you know what I mean. They're the same Ft's. Therefore, computer's a little laggy today. I have 68.8 newtons minus 7 kilograms times the acceleration is equal to the other tension, which is 26.8 newtons, plus 3 kilograms times acceleration. Time to combine like terms. We have a 7A and a 3A, which is going to become 10A. And I can subtract the 26.8 over. That's way too convenient in terms of how clean that cleans up. That's 42 newtons equals 10A, well, 10 kilograms times A, and acceleration is 4.20 meters per second squared. Weird, when I did it before this, I got 4.18. I wonder. Anyway, after that, we are set with a little bit of kinematics that we're supposed to do: initial velocity, final velocity, acceleration, distance, and time. And I believe the system starts from rest, and we're trying to find the amount of time it takes to move 0.5 meters. Remember, we said whichever way it was moving is positive, so that's kind of helpful. So it's 0 meters per second. The acceleration we just solved for, 4.2 meters per second squared. Distance is 0.5 meters, and we're looking for time. That is all about math rep number 3. You know that by now. You're pure geniuses. You've survived this long. I don't know how. I take full credit for it. Without me, you wouldn't survive. Don't know what I'm talking about. Math rep number 3. We've got 0.5. This goes to 0. How convenient. Equals 1/2 the acceleration, 4.2 meters per second squared times the time squared. And I get delta t is, that's interesting. Now, my old answer was 0.489 seconds. I'm not sure if it's exactly the same because my acceleration was different before. But that's basically it. That's the strategy. Would you like to hear it again? Okay, let's do that. Here it is. For each object, you should be drawing a free body diagram. That's the first thing I would do. And then the next thing I would do is label the direction of motion as the positive direction. That's key, because if you don't, you might end up with an answer that's negative 9.8, which makes no sense. That means it's falling and only gravity acts on it. That's not true. There's ropes touching the masses. You do the sum of the forces in X and Y for each object, and remember that the acceleration for each object must be the same and the tension for each must be the same. So you can either isolate your FTs and set equal, or you can isolate one of the FTs and you could substitute in. Once you have that, you could solve for acceleration, and you might have to do a little kinematics. Now, There is also a shortcut, or what's considered the systems approach. This is mostly for my AP people. However, it is for everyone. AP I mentioned mostly because the multiple choice, you're expected to know this shortcut, and sometimes it's allowed on the actual AP exam. For both classes, you are not allowed to use this method for our in-class tests. You must use the longer method. Unless it's multiple choice, then you can use the shortcut. The shortcut is interesting. The shortcut is to draw a free body diagram of the forces acting on the system that cause the system to have a change in velocity. In this case, that is going to be the force of gravity pulling down on the 7 kilogram mass. We also have FGX acting against that motion for the 3 kilogram mass, and we have the force of friction trying to prevent that motion as well. The normal force and gravity, I should say these two, the normal force and FGY, they are not doing anything to accelerate or change the velocity of the object, so they are not relevant. Also, some of you might say, well, what about the rope? I love that you're thinking that. It's a great question. You've got tension pulling this way and tension pulling this way. I don't know why I wrote FN. So the problem is, or the issue is, yeah, they're both tension. They pull in opposite directions. One's going with the motion as a 3 kilogram mass goes this way, and one's going against the motion as the 7 kilogram mass falls. So they're acting in opposite directions on the system, and they're equal and opposite, therefore they don't matter either. The net force on the system is 0. Now all we do is the sum of the forces up for the system. Okay, so we already did the forces in the Y before. Some of you are getting good at this, knowing that for the mass on the incline, we got that the normal force was equal to, I'm so sorry because I didn't write it down, so this will not be edited and you can hate me later. What did we get? 22.5. I thought that's what it was. Come on. I'm sorry to waste your time. I hope you're playing this at 1.5 speed. So we got 22.5 newtons. I needed that because I know of the friction force here. I'm going to have to do mu Fn. So here we go. We've got light blue. I don't know. We're going to sum the forces that cause the entire mass of the system, I want to stress that, to accelerate. We have Fg on the 7 kilogram mass trying to make the system move. Then we have FGX on the 3 kilogram mass and friction acting on the 3 kilogram mass, trying to prevent the mass of the system from accelerating. Okay, this is so much better when it's algebraic. So here we go. Let's throw some numbers in here. For the 7 kilogram mass, we have 7 kilograms times 9.8 meters per second squared, minus FGX, which would, on the 3 kilogram mass, that's 3 kilograms, 9.8 meters per second squared, sine 40. Minus the force of friction, which was, I believe, 0.35. Is it 0.35? I hope it was. Times the normal force, which was 22.5 newtons, causing the mass of the system. The system total is 3 kilograms plus 7 kilograms, or 10 kilograms. And the only thing we don't know here is acceleration. So this is kind of a shortcut. And we can get right to the acceleration right away. I'm going to put this in my calculator really quick. 7 times 9.8. I just want to see if it's the same as the other one. Sine 40 minus 0.35 times 22.5. Enter. Divided by 10. Yeah, and this time I got acceleration is 4.18 meters per second squared, which is definitely less than 1% off from my other answer, which was 4.2. So that's the strategery for the shortcut / system approach. Again, you want to draw an FBD of the system. You want to label the direction of motion as the positive direction. And then you want to sum the forces that cause the system to accelerate. Only the forces that are causing the system to accelerate. The tension's not doing it because they cancel out. They're equal and opposite. Normal is perpendicular to motion. FGY is perpendicular to motion. They're not changing the velocity. And again, the direction of motion is positive, which I failed to label here. So this is moving this way. So anything that helps move that way is a positive force. Anything that is against the system moving that way is a negative force. That's about it. That was a rather long video, but I hope it was helpful in some way, shape, or form. And I would give this puppy 3 out of 5 stars just on length alone. Wouldn't change a thing.